thank you for inviting me here. So I'll be talking about functional bootstrap and this setup in the system for boundary CFTs. So the functional bootstrap was introduced by Miguel Paulos and Dalimil Mazak. It has been mainly last year, and the idea was built on something called extremal functionals. And the good thing about functional bootstrap, as I'll explain later in my talk, is that they give a this method makes manifest our analytic understanding of the CFT spectrum, and it's obviously it in a way it probes the whole crossing region for whole crossing region, and it also and by doing that it gives a more powerful system of equations even for numerical bootstrap. So it's both a good it's a good method for both numerical and analytical way of doing things. So their method was mainly in one dimension, but I will explain this for the system of boundary CFTs, and I will start with an introduction to boundary CFTs. And another good thing about analytic functional bootstrap is that it makes a direct connection to what is called the Polyakov bootstrap. I believe that we have seen a couple of talks for Polyakov bootstrap in recent times by Anindya and Kaushik. So I'll try to make this connection also very clear. And so I'll start with introductions to boundary CFTs. Then I'll give a short introduction to the Polyakov bootstrap itself. Then I'll try to give a setup for Polyakov bootstrap for the boundary CFTs. And finally, in the main second half of my talk, I will talk about the functional bootstrap setup. So let me begin with boundary CFTs, boundary bootstrap. So for boundary CFTs, we have, let me draw a picture for a CFT in a regular space-time, and let me split it in half by inserting a line, and let me label my coordinates in this way. So I'll label my coordinates x as x parallel and x perpendicular, where the direction where the distance from this boundary I will call x perpendicular. So this direction. You are in general dimension? I'm a general dimension. And yeah.
4-dimension one boundary?
Yes. Yes.
So this x perpendicular is a vector?
Yeah.
I'm sorry.
It's a direction. It's a
x parallel is a vector. So x parallel is a vector, and x perpendicular is just one.
Yeah. Yes. That's it. Sorry. Yes. So when we have a system like this, the CFT here is broken. It has a broken conformal symmetry. And on the boundary itself, we have a full conformal invariance. It's a regular CFT. So the easiest thing to consider in such a setup is two-point function.
So when you say broken conformal symmetry, it is broken precisely the subgroup that preserves the.
Yeah, it preserves the conformal symmetry over here. Yeah, so it's d to d minus 1.
That you make a conformal transformation which does not move the boundary.
Yeah. Yes.
So
yes.
It fixed point wise. Sorry, set wise.
Sorry.
We'll keep this fixed set wise.
Yeah. Right. Yes. So the thing that we need to consider here is a two-point function and two-point function like this. Sorry. 2-point functions. So I'm considering a 2-point function of scalars, and in this talk I'll be focusing on only scalars, phi. So, and this 2-point function, since the conformal symmetry is broken, will not have the usual regular structure that we know for a CFT. It will have a generic structure, g of z over x1, x2 to the power delta phi, where delta phi is the conformal dimension of phi. And z is an invariant.
X1, X2, or X1 minus X2 or X1?
It's x. So I'm sorry. It's x1, x2, x1 times x2, but these components are perpendicular components, and it's x1 and x2. Okay. And this invariant cross ratio, there's just, and you see that there isn't just one cross ratio that I have written. So that's the feature of the boundary CFTs, that you have just one cross ratio for a 2-point function, and it is given by 4 x1 perpendicular, x2 perpendicular by x12 perpendicular parallel square plus so this is the expression for z's, and yeah. So a reference for this can be found in Rastelli et al. From 2012. Okay, so how do we find? What can we say about this guy? What can we say about g of z? So there are two different ways for computing the correlation that this 2-point function. One is we know that the usual operator product expansion for regular CFTs still hold for the bulk. So when I say bulk, I'll refer to as this part of the system, and I'll refer to this as the boundary. And if we use the operator product expansion in the bulk, we get one way of expanding g of z. So we can use the bulk OPE, which is given by, which is basically phi times phi given by delta O, where delta is a bulk operator dimension. And if we use this operator product expansion in the 2-point function, so you can use this operator product expansion in the 2-point function, and then g of z has the form c of delta times g of delta times. So what just happened here? I used this OPE in this 2-point function, and then I got what I got would be so g of delta is basically a sum over 1-point functions of O, and this 1-point function. So I got this 1-point function by inserting this OPE in this 2-point function, and this 1-point function is not going to vanish because symmetry is broken. So what I'd get is this guy is gz, g of delta z, which I call bulk block, and its value is, and it can be written as a 2-point function. It can be written as a 2f1 function evaluated at 1 minus z. So this is one way of expanding the 2-point function, and there's another way of expanding the 2-point function. It's called the boundary.
Does
Sorry?
that 1 minus z to something?
Here? Yeah, there is also a power answer, yes. There is a 1 minus z to the delta by 2.
And this 2f1, is it just this delta to the the standard thing?
2f1, it's
The arguments, the parameters?
I think it's a standard thing, yes, if I remember correctly, and it's
Delta.
yeah, but I think there is a so yeah, let me just write it down. And this argument is delta minus yeah. Something
And
like that.
only scalars contribute to it?
Yes, only so yeah. So as Abhijit pointed out, this sum to this sum, basically the sum for these 1-point functions, the contributions will be only scalars. So there is
The
no.
1-point functions of all spinning vanish. The 1-point functions of all spinning operators vanish.
Yeah, the 1-point functions for all spinning operators they vanish.
So that can be understood from the amount of breaking of the conformal symmetry?
Yes. So the easiest way to explain this, I think, is that so when you write a 1-point function of O, so it's something like some number by x perpendicular to the delta phi or something like that. And there is no way you can write for a tensor structure, for a tensor operator, there is no way you can write something like that with indices and its transformation properties. So that's why they have to vanish.
So
Because there is no, because then you also have to write a structure like this with indices. And that there is no way to, with the correct transformation properties, there is no way to do that.
But that can be also seen probably just by looking at the transformation properties of the 1-point function of the stress tensor or some spin 1 operator.
Yeah.
The Lorentz transformation properties of that.
Yeah, but yes, that's something like that. But 1-point, it's a 1-point function that you need to write in some certain way. That, yeah.
So, I mean, the way you would figure this out, for example, in case of 3-point functions, you arrange the 3 operators on a line, and that preserves only SOD minus 1. So only SOD minus 1 singlets need to be only SOD minus 1 needs to be respected, and that's why a spin L operator would also contribute, right? In the 3-point function of a scalar.
Usually.
Yeah.
Yeah.
So here also, if I do the same thing, here I have this boundary, and I put 1 operator.
Yeah.
Now the symmetry that is preserved by this is this line that is perpendicular to
Right.
this and passes through this guy, right?
Yes.
And that preserves only SOD minus 1.
Yeah.
So shouldn't spin L also, in other words, spin L with index which is in the perpendicular direction should have 1-point function? No?
Okay, so the most rigorous way it was explained in this paper was the following way. It's that so what they did was, so they tried to write this whole thing in embedding space.
Yes.
And in embedding space, if you have to write tensor structure, then you have to take care of things called there is this property of transversality. So and what they showed was, even though you can write in a so as you just said in a nice way, you can perhaps you can write something like v of z, where v is the vector in the perpendicular direction, v dot z times L times something like v dot p to the power delta phi or to the delta. So they argued that this structure, this is the only structure that you can write, but this does not satisfy transversality. So it's a property that so it's like a p dot O in embedding space formalism should, sorry, p dot O is O, yeah, OA, PA dot OA should be 0. So, and it's required to define the tensor structures in embedding space.
direction which is along the this.
Oh, sorry. No, actually now we can understand this. So, you're right. So the most amount of symmetry, to see the most amount of symmetry that you preserve with the configuration, you should work actually on a sphere. Okay, that's why in ordinary, without the boundary, you have 2-point function, one you put at north pole, the other you put at south pole, and that preserves SOD.
Right.
So that's why only singlets, only this will click with something that is forming SOD singlet. Now for a 3-point function, you have another guy which will isolate on a line. What is it called? This latitude or whatever. And then that would have SOD -1 invariance, and then you would have spin L guy would also contribute to that. But now in this case also, if you want to preserve do this in the most symmetric configuration, you should look at a sphere, cut it, and without loss of generality, that cut could be on the equator. Okay, so that's a hemisphere. And now the operator could go on the pole. Okay, and that configuration clearly preserves SOD.
Okay.
Right?
I see.
Because if you have a hemisphere and a thing at a pole, this preserves SOD, and then you will not have any
I see. Okay.
spin L guy sitting there.
Okay.
2D CFT is certainly true because purely holomorphic operators, they don't have an image.
Right. Exactly.
So, so you need an O times O bar kind of structure, so that the O bar comes here, and the 1-point function of O bar becomes a 2-point function of O and O. Now, purely holomorphic operators, they don't have this operation. There is no O bar.
Okay. So let me continue. So the next thing that I was about to say was the boundary channel expansion. So the other way to expand this 2-point function is to note that every bulk operator phi allows an expansion in terms of operators on the boundary CFT, on the CFT that is there on the boundary. So we have something like phi, which can be written as a sum like this, x parallel times a sum like this, where this sum is over boundary operators. And so what I'm going to do now is, and so this structure of F can be determined from conformal invariance. So it is something that is known. And so what I'm going to do is I'm going to insert this in the 2-point function, and then I'll get a sum over 2-point functions of the boundary operators, which is determined, which is something we know, which is the usual 2-point function. So we get another expansion for GZ given by in the following way. C hat of delta hat so where G hat is called a boundary block. And it is also a 2-point function. It's also a 2F1 evaluated at Z. Here we can have anything. Yeah. Okay. And the statement for boundary bootstrap is that these two expressions, these two things should be equal. So we have a sum over bulk blocks, bulk operators, C of delta, G of delta, Z equal to sum over delta hat, C hat, delta hat, So anything with a hat is basically related to boundary operators. So C hat is the coefficients for the operators in the boundary. G hat is the boundary block and everything. So just keep that in your mind. And the unknowns are these guys are the unknowns. So when we solve it, we have to solve for C delta, C hat, and delta hat. Okay.
So now the delta set of operators has a spin also, right?
Yeah. Yes.
And so d minus 1 spin.
Yeah. Yes. Yeah. So can I erase this part of the board?
These blocks are known in closed form for any
Yes. Yes. Yeah.
So even the G hat is known for any dimension?
Yeah. Yes. Yeah. It's because it's just a sum of 2-point functions. So this 2-point function is known. It's easy to compute.
So the sum of 2-point functions?
I mean, so I used this guy in what I erased in this 5, and so it basically it becomes a sum.
I mean, any block in that sense is a sum of 2-point functions.
Yeah, right.
Even the bulk block, right, in any dimension is a sum of 2-point functions. You do OP on both sides and do is that okay?
So here it was a sum of 1-point functions of.
No, I mean the standard.
Yeah, that's
standard
right.
But that doesn't make it solvable.
That is true. That is true. Yeah. Right. I think here the structure is simpler.
Maybe the fact that there's only one variable makes differential equations.
Yeah. Yes. Right. Okay. So now I'm going to write down one well-known solution to this equation. So just so this is BCFT Bootstrap. One solution to this equation is the generalized free field solution. So the GFF solution for this case is okay. So before that, so there's one more thing that I need to specify. So when I'm solving this, so I have to keep in mind.
I'm sorry. So when you say that you're solving this, what do you mean? I mean, which side is known, and which part of what are you trying to solve for?
Yeah. So I'm in my talk, I'll be mainly solving for C delta. These are unknowns, the delta hat, and the C hat, and I will take as my input the bulk dimensions, delta. So actually, so in this paper by Asteli and others, they actually solve for everything. They actually solve it. They try to set up a numerical way to solve for all these things, even delta. Find all possible sets to constrain the set of all possible all these 4 things. But
is that a constraint problem?
sorry.
I mean, if you don't take anything as an input,
Yeah.
there's a solution. Is this equation constraining enough? Because usually
They had some.
unitarity
Yeah.
plays an important role in constraining
Yes.
the space of
Yes.
solutions, right?
Hmm.
If I don't impose unitarity on the general bulk
Right.
bootstrap equation,
Yeah.
I can probably write infinitely many.
Sure. So it's one important input that should be missing is whether these things are positive or not.
So in that case,
In that- yeah,
they impose some
They
unitarity.
impose that these things should be positive, and that corresponds to some boundary conditions, some certain boundary conditions.
Not unitarity.
Um, I don't think that was unitarity, if I remember correctly. So this corresponded to some boundary conditions. So basically what you have to do is input delta and also boundary conditions.
C delta are the OP coefficients
Yes.
don't know anything about boundary condition. So sorry, what is the issue of boundary condition?
That I'm not very sure of what happened in this.
Like C delta is unaware of the existence of any boundary.
C delta, no. C delta is the OP coefficient as well as the product. I mean, product of OP coefficient is the
No,
OP
see, yes. This is a different C delta. I mean, this is not the usual OP coefficients.
It's product with 1 point
Yeah.
function, right?
Yes.
So you
But
make an operator.
I thought the 1 point function is isolated as a G delta of Z.
No, that's the block. That's the
That's, yeah.
Oh, I'm sorry. So there is a curly G. Excuse me. I see. Okay, got it.
Yeah.
So the curly G. I see. So C delta. Oh, I see. Okay, got it.
Mm.
So it goes more.
Yeah.
But C hat delta hat would be positive from standard
It's-
unit.
yes,
angle,
yes.
Standard unit.
Yeah. Right. Okay. So there are two things mainly that are.
Square of real number.
Yeah. Yes.
But in the searches, is there some kind of a like truncation that you can
There-
search up to some
I guess so. Yeah.
delta and so on and so
Yeah.
forth?
Yeah. Yeah. There is some truncation.
That kind of truncation is allowed by the equations, and that's sort of understood.
Yeah, I think so. Yeah. That's allowed. So usually.
Yeah, usually one doesn't allow for truncation of equation to some delta, right? That's this EOC method, right? I think there is some paper, I don't know whether that's what you will be talking about, but there are some papers dealing with some truncation. Truncation, if you truncate the spectrum, this equation requires infinite operator. You can do that.
Yeah, that's
Hmm.
So if you truncate it, you cannot solve this equation. So the approach that you have to take is the failure of the equation. You minimize that with a truncation, and that goes close to the actual solution. This is the
Yeah.
kind
Right.
of way
This is
you
the.
can think about the truncated solution.
Yeah.
It's
So
a-
all the higher guys somehow can be thought of as more and more insecure.
Yeah. Right.
I don't know why. I don't think it's understood why.
But I think
Yeah, that
there's.
is what I remember from the original talks of on
Hmm.
Bootstrap.
This is the usual thing that
Yes.
one operator here is reproduced by the infinite hours.
Yeah, that's the standard. Right?
Yeah.
So from that point of view, you need infinite.
Yeah, right.
But for numerical, it's a standard thing to do that. There is a truncation that there is somewhere. Okay. So the GFF solution. So yeah. When I say boundary conditions, I usually mean one of the two things, either Neumann or Dirichlet. So the GFF solution is given by the following. For in the bulk, I have the following operators: delta equal to 2 delta phi plus 2n. That corresponds to operators of the following kind: phi of box to the power n phi, and then I have boundary operators, and that depends on what boundary conditions I have put in. So for Neumann, which corresponds to phi, equal to 0, I have boundary operators. I have delta hat equal to delta phi plus 2n, which corresponds to operators of the kind phi, and then I can have Dirichlet, which is phi at x perpendicular equal to 0. Where the operators are. This is the GFF solution, and it's going to play an important role in what I'm.
So why not spin in this delta hat?
So in this case, we don't have spin because so I guess so the GFF solution is given by the something like x1 minus x2 to the power delta phi plus or minus 1 by x1 minus x2 to the x1 minus x2 r. So r is the image of x2 to the delta phi, and when you decompose this, there is you don't see spin. So this is enough to decompose the 2-point function.
This is specific to this boundary condition. In general, you will have swing.
I think so, yeah. In general, for any interacting CFTs, yes.
Why not here? Okay. Also, is this input necessary, or can you just work with the bulk input about dimension? That would then
Yeah,
allow you to find all possible boundary conditions.
So sorry, can you specify the thing?
Put just the bulk dimensions.
Yeah,
So your bulk theory once and for all is a GFM,
yeah.
but boundary, let's say you don't know what it is.
Right, yeah.
Then
So
that would allow you to classify boundary conditions.
yeah. Yes, sure, yes.
And are there more than just these?
There's other boundary conditions, you mean? Yeah, there are some. You can have something like the interface boundary conditions also. Yeah, where you can maybe some mixture of these things.
Then will delta hat have spin? Or
I'm not sure. I think so. Yeah.
So plus minus is what?
Plus minus is-
plus minus.
Why is there a plus minus? It's so that since these
I see. Minus is for Dirichlet.
yeah, so it's just to make these things vanish. Okay, so so this was all about boundary bootstrap. So now I'll say in short how to set up the Polyakov bootstrap for this system.
So I have a question.
Sure.
If instead of the generalized free field in the bulk, you just have free field
Here, free fields.
in the bulk.
Yes.
Yeah, there also you can talk about this.
Yeah. Right. But then they'll have
So the bulk
even
operator
lesser.
is only one.
yeah. So for free fields, we have if it's free field theory, then we have just
I square of.
phi square. Here I will have I think for Neumann, I think I'll just have n equal to 0, and here also just n equal to 0, if I remember correctly.
Why equals 0 there?
Sorry.
Why does that? I mean, I would think that the bulk spectrum it just has one operator, but why does boundary spectrum also have one operator? Right, that would be difficult to imagine, right? Because you have a block, a single block. The correlator is a single block then, right?
Right.
The bulk channel given by f squared, and then you want to decompose it into a different set of functions. You would need infinite.
Yeah, I have to maybe I have to check this again. But if I remember correctly, I think for free field theory it was indeed just one operator that could reproduce this full function. I mean, this full function was something like this replaced by d minus 1 by 2, and yeah, I think. But I have to check that. I'm not. I can't say for sure, but I think it was just only one.
That truncates because box is 0, right? But here this is del perpendicular squared.
Yeah. Right. There's no need for this to be 0, but still, I think it is just that only one was necessary to reproduce this thing.
No, so that goes into more like what Abhijit was saying, that don't put these things as inputs, the delta hats. Just determine all of them, because your argument is like that. Okay, you find out what the 2-point function is, okay, and and from there you try to derive. So you're essentially you're saying I look at the expression and I see what delta hats contribute. There is no intrinsic argument to say that there is only one operator. It's just that by looking at it, okay, you find that only one operator contributes.
Right. Yeah.
But isn't that what is being done? Like, I mean, he imposes the boundary conditions and then tries to solve for this crossing equation. Automatically finds.
But it seems from this description that he's putting in delta hat equal to delta phi plus 2 etc.
That I mean.
Oh, that's a result.
That is a result. I mean, this is a solution. I'm giving you the solution.
Yeah, no, you're putting it in. You're putting that in, right?
I mean,
The list of delta hats is your result.
Yeah, it's a result. I'm just giving a solution, and I will use this solution later for my setup. I mean, for the.
Yeah, that's how I
Oh, that's the logic. I see it.
Yeah.
So he's inputting only the boundary conditions, and as a result of which he's finding the
Yeah.
solution of the crossing
Yes.
equation to be
What
satisfied.
does it mean input boundary?
So he's.
I mean, I'm
inputting
assuming that.
this-
I'm assuming that I have either boundary or Neumann,
Yeah.
and
What does that mean? So that you are assuming this delta hat to be that or that, right?
I'm assuming that delta hat to
No,
be.
delta hat is a consequence
I'm
of
assuming that this is either this is true or that is true, and yeah.
That's how.
And basically, it also means well. So this result is mainly obtained from
Wait.
looking at.
So you are imposing this BCFT bootstrap, right?
Yes.
In which now you are saying that you will determine whatever you can from the bulk,
Yeah.
including the boundary condition, and
Yeah.
you are finding out the whole list of delta hats
Mm-hmm.
by solving this bootstrap
Yeah.
equation, right?
Yes.
And that's your list of delta hats.
Yes.
Right.
Right. Yeah.
That's what- So this delta hat is a consequence of that. You are not doing that.
But I mean that I'm. Yeah, that's right.
So
Are you
is
finding
that-
all possible boundary conditions?
So just
No.
There are many solutions to this, of course.
yeah, depending on the boundary conditions. He's just looking
No,
at
but
the
okay,
boundary.
you say this is a boundary condition,
Yes.
del plus phi equals 0. How do you put this in that equation?
That I know.
Oh, so, I mean, by that I mean when I'm. So if there is an operator like if there is an operator like delta phi plus 1 for non-boundary condition, I will just put c delta equal to 0. That's all I mean. So that is that understandable? Yeah. Okay. I wrote this down because I'll use them in the functional setup. Okay, so Polyakov. Bootstrap. So yes, I won't spend. I hope not to spend too much time on the Polyakov Bootstrap setup, and certainly So I think you already know a bit of the what it is for the usual CFTs because you have heard numerous talks and also mainly 2 talks in recent times. So just in short, the claim of Polyakov Bootstrap for usual CFTs. For the usual CFTs is the following: is that we can write a 4-point function of scalars as a sum over Wheaton exchange diagrams. Plus contact, and this will give you the usual OPE plus unphysical double trace blocks, double trace operator blocks, and you equate these terms to 0, and that gives you the Polyakov Bootstrap equations. So I will try to do the same thing. But before that, there is one thing that limits the applicability of this whole thing, is that we don't know how to fix the contact diagram in this basis. So this contact diagram is basically amounts to an ambiguity. So, and if we try to do perturbation theory on this system of equations, we run into problems at higher orders of perturbation because this thing is important to fix. How to do this for boundary CFTs? So for boundary CFTs, for BCFT, we need to do this whole thing. We need to write down tree-level Witten diagrams, equivalent counterparts of these guys. So what I'm going to do is the most basic thing that one can do is that for the CFT in D dimension, I'll consider a bulk ADS in D+1, and for the boundary CFT, I will consider an ADS in D dimension, and I'll try to do some tree-level exchange processes in this thing. So how to do that? What are the possible tree-level exchange Witten diagrams that one can write? So one can have bulk exchange diagram that I will call W delta, and this is something like see if I have 2 points here, so these 2 points will meet in the ADS D+1 and exchange an operator that interacts with the boundary. So yeah, and while doing that, I need to take care of the following things. Is that the propagators, these are the usual boundary to bulk propagators, and the vertices, and this is a bulk to bulk propagator. These things should satisfy Casimir equation and the boundary conditions. So this vertex, so in constructing this diagram, I have to take care of the fact that the vertex and the propagators should respect boundary conditions. So this is a bulk exchange Witten diagram, and then I can have a boundary exchange Witten diagram.
The endpoint on the ADS D minus 1 needs to be integrated over?
Yes, right. Then I can have a boundary exchange Witten diagram which looks like the following. I have 2 points that comes and ends on the boundary itself and exchanges an operator on the ADS-D. So, and there is an exchange of operator delta hat, and I'll call this process a W hat of delta hat. Finally, the final tree-level diagram that I can have is a contact diagram, which looks like the following. And I'll call this I'll call it WC, contact diagram. Now there are some nice features that these contact diagram, these Witten diagrams satisfy. They are the following. So for W, so W hat, W for the W, so you can decompose the Witten diagram in certain channels for different values of z. So all these are functions of z's. For different limits of z, you can have different decompositions of w, and so there are so it allows a for the z going to so for the z small z limit, wz has the decomposition which is called the boundary channel decomposition, which is given by the following. And also for the z going to 1 limit, we have the bulk channel decomposition, which is given by t hat. I'm sorry. It is here. Tn g 2 delta phi plus 2n plus g of delta. So these are the two different decompositions that the Witten diagrams allow for two different limits of z's. Okay, and for w hat, there is a similar thing. It is for z going to 0, we have something like g hat of delta hat plus a plus the similar things, similar decompositions. No, there's a derivative. No, none of them. No. Finally, I have this WC, which is I can just write it as AC of n and plus BC of n equal to TC of n. Similar decomposition for the contact diagram. So when I'm yeah. Is there a way to understand?
Derivatives is what you could think of as giving animals, right?
Yeah, that's right. So actually, I'm not sure how to. I don't know what a good reason why the Witten diagrams don't show the derivatives. But yeah, since there is no derivatives of bulk blocks, I would have to take the bulk dimensions as my input.
So in the standard Witten diagram,
yes,
without the boundary,
yeah,
the H-channel Witten diagram, when decomposed into H-channel blocks,
yes,
has derivatives or not?
yes, it has. Yes.
And when also decomposed into T-channel, it has derivatives.
Sure.
Right?
Yes.
Both channels.
Yeah. But here they don't have it, unfortunately, and that's a little problem, and that's why you have to take the, as I said, the dimensions as input. Otherwise, we could have solved for everything. Okay, so the Polyakov bootstrap ansatz is going to be that phi of phi can be written as sum over c delta w delta plus delta hat c delta hat w. Yes.
Sure. But let's say you solve this
Yeah.
equation, okay, using your Polyakov bootstrap.
Yeah.
Now you add Wilson Fisher. You add an epsilon perturbation.
Right.
That's what problem. But I'm confused because the other ansatz are flexible enough to admit the anomalous dimension of the bulk operator, right?
Other
namely the derivative of the block enters, right?
by others,
The
you
bulk,
mean
just the bulk without
yeah,
boundary,
yeah.
right? But here you were never going to get anomalous dimension for the bulk operator.
Yeah, exactly. Those are inputs. I have to.
You are taking fixed that, right?
Right, yeah.
But Wilson-Fisher theory clearly has a richer structure.
I mean,
So I'm talking about, let's say, Wilson-Fisher fixed point
yeah.
with a
Boundary, yeah.
Let's say the Neumann or Dirichlet boundary.
Right, right.
Something like that. This
Yeah.
is the kind of setup I have.
Right, yes.
Is Polyakov bootstrap going to give me solution to that?
Yes, but you have to, I mean, take into account, you have to assume that you already know the anomalous dimensions for the bulk dimensions.
But
They are-
usually the bulk dimensions are also fixed as infinitesimally away from the free generalized free point.
Right, right.
And that is thought of as anomalous dimensions.
Yeah, so you have to know, it isn't that we
You want to
know
take those
the,
and write it as fixed.
yeah.
I mean, not anomalous, but actual dimensions. You cannot solve for those.
I mean, I'm saying that you have to take the input of anomalous dimensions as well. That's what I'm saying. So the input is that delta equal to 2 minus 2 by 3 epsilon plus whatever epsilon square and so on. So this whole thing is an input. Yeah. But that's how it's usually done in all the analytic papers.
The kind of thing that you do with the, not with the boundary, but
The usual.
in the usual way, you find for, you solve for this and you
Yeah.
find this epsilon correction,
Of course,
right?
yes.
Because you have derivatives.
Yeah, that is right. So here you have to assume that we already know those things. So you can solve for everything.
So now you have to know the bulk theory.
Yeah, you have to know the bulk theory. You have to know the bulk. Yeah.
Only then can you talk about boundary conditions.
Right. Yeah. So both the analytic the analytic functionals as well as the Polyakov bootstrap, this is unfortunately the case. Okay. Yeah. So when you do that, so here I will just say that there is no contact diagram, and my Polyakov bootstrap equations are going to be something like delta hat times a of a hat equal to 0, and then there is similar equations for b hats. But this system of equations, when you try to solve at epsilon square, so I will try to solve this equation for the Wilson-Fisher theory as we just mentioned in d equal to 4 minus epsilon, and it's observed that at epsilon square there are some mismatches. And these mismatches basically come from the polynomial ambiguities, and one of my goal is to fix the polynomial ambiguity.
So what is this A hat and B hat?
A hat and A hat are these guys. Okay.
Is it true in the bulk case, these polynomial ambiguities are fixed by the Rege bound?
So these things will appear now. Yeah, from functionals, you will see that the Rege boundedness for the blocks are important. So now I'm in the last 30 to 40% of my talk. So how much time should I be having? Okay. Okay. So now comes the last part, which is the idea of functionals. So the idea of functionals is the following. It's that suppose you have the usual bootstrap equation. Suppose you have the usual bootstrap equation, which is a sum over C of delta f of delta equal to 0. So what you do is so the thing that you do is identify a basis for expansion for the f's and write a corresponding functional for solving the system of equations. So what do we mean by that? Is that what is the basis for the numerical bootstrap? We know that the usual thing that one does is expand the equation in terms of derivatives, right? So how to identify a basis corresponding to that? So the basis for the numerical bootstrap is just the following: is that you have fz, and you expand fz, and you write fz in the as an expansion of z to the power m and z bar to the power m's, and the coefficients of the expansions are the derivative blocks themselves. It's like a Taylor expansion. And
so this is done at half usually, right? Or
sorry?
you want to do this at 0? Or
Yeah, right, at fz equal to 0. So yeah, around the z equal to, around z and z equal to half. This is z and z equal to half. And the usual and the functional that corresponds to that corresponding to that is just a label name as omega I, is the set of derivative operators. And so when I write them like this, the bootstrap equations they become something like C delta of omega I acting on F delta equal to 0. So from here I obtain a system of equations for an infinite system of equations for the bootstrap. But okay, so and now comes the motivation for the analytic bootstrap. So this, just let me mention it verbally. So there was a work by Cheryl Schoch and Miguel Paulos, who introduced the idea of extremal functionals. So the idea of extremal functionals is the following: is that if you have if you know a system, if you know a complete solution to the bootstrap equation, if you know the complete solution of a bootstrap equation, which is like the following: C delta and delta, a solution, you can by hand you can construct a system of equations called the extremal functionals. And which these extremal functionals correspond to, these things basically correspond to the limit of infinite derivatives of the numerical bounds. Infinite derivatives of the numerical bounds. And they have the power that they can probe the whole crossing region. So even if they come from the numerical bootstrap, they can essentially probe the light cone limits, even the light cone limits. So in a way they are more powerful. So I don't want to go into the details of the extremal functional things, but the question that one asks now is that, can we construct functionals that are built on an analytic understanding of the spectrum? And
this extremal functional you obtain if you know a solution, some solution.
Yeah.
That is usually the generalized Free solution.
No, that is here. I think those are the numerical bounds. I'm going to do that now, the generalized Free solution, but that's the question that I'm going to ask now. But so the first external functional paper was just the numerical bound that they obtained for the Ising model.
No, but you say that this extremal function will come about once you know a solution to the bootstrap.
Yeah.
What is that solution?
I think they were talking about, the first paper was for the numerical bounds. They didn't really have a solution. They were just talking about numerical, the optimal bounds of the.
No, but what is the extremal functional that they use?
So the functional that they constructed were some integrals of some discontinuities of the blocks, and those those functionals, they kind of trivialize the optimal bounds. But I'm not very, I don't know that work in very detail. So I'm just trying to mention this in as a motive.
Regarding the external function thing, so I can take any function you give me, I can write it down on the basis of derivatives,
Yeah.
right? So then you can put like random coefficients in front of it. It doesn't have to be a Taylor standard. You can
Right.
put some random coefficients in front of it, and then you can vary those coefficients and see what gives you the smallest, the smallest left-hand side, which is C delta W I. This thing equals.
Yeah.
Is that what an external functional is?
I don't think so. So external.
So then what is an external?
So I think the construction for external functions was something like it was argued by a paper by Dalmil Mazak that it has to be of the form discontinuities of f, discontinuities of f with some kernel hz, and where hz satisfies some properties. But I really don't want to. I don't know those papers in very detail. I just mentioned this for some motivation for what I'm.
I'm just not able to answer the motivation. So
The motivation is the fact that once you that you can believe me for what I'm going to say. The claim is that once you know some solution, you can construct some basis, and that would correspond to some nice functionals, which will probe the whole crossing region and will also make manifest the solution. It is nice to have that solution to be our analytic understanding of the spectrum. So I will for this I will use the GFF, and then I'll try to identify a basis, and then I'll construct the functions corresponding to that. So you may forget that so this corresponds to a paper. I'm just trying to say that this is a flow chart that I'm going to follow. So what I'm going to do now is I will try to, yeah.
So at the end of the day, we did some function. It will admit some basis in terms of this omega also. But you want to work with finite number of equations.
Right.
So which choice you make for the functional is important. So this is better.
I mean, and it is extremal in what sense?
It manifests the extremal bounds, the optimal bounds.
So the extremal has to do with whether or not it's able to reproduce some.
Yeah. Yes. Yes. So.
Okay. So sorry, can I just say that again so that so what you're saying is that like if I take the first equation C delta F delta 0, then I hit that with any functional. If it's an infinite sum, I hit it with any functional, it will still give me 0, right? But now you're saying you work with a truncation, and when you're truncating it to certain orders, then of course there is a question of like which omega i's, which basis of which sort of lead combination is optimal.
Yeah, because that one, for example, probes probes the region near half, right?
Yeah.
So if you use 15 of them, you will go a little bit.
Right. Yeah. Here you have everything.
This guy somehow has some integral.
Integral that.
So it's a sort of
Yeah,
All the
I don't
infinite
know
derivatives.
analytically what it means to be extremal.
But yeah, you're right. That basically corresponds to taking an infinite number of derivatives all together.
Are you going to give us an example of this external?
No, for their case, no. I'll give you examples of what I know for the recent papers. Okay. So I'll show how to do this systematically. So for the solution, I will consider the GFF solution. I will try to identify a basis of expansion for the conformal blocks, and I will try to construct some functionals, which I'll call the analytic functionals. And and I'll show how to construct them. Okay. So these analytic functionals, so let me also mention some properties of the analytic functionals. So they have the following properties. They have to trivialize the GFF. They have to be finite on blocks and correlators. And also, they have to have the properties of swapping, which is a simple property that omega acting on sum of g's is equal to sum of delta on omega of g. This is the property of swapping. So I have to take into account that they satisfy the following things. Okay. Now, first thing is how to identify the correct basis. And I will do this whole thing for BCFTs, by the way. So I'll do this whole thing for BCFTs. Okay. So for identify the basis, look at the following system of equations for the Witten diagrams that I already wrote down. For the system, for these equations, let me just do some exchanging of terms. Let me bring this term on the left-hand side. So I have something like this equal to that. And let me bring these two terms from this equation on the right-hand side. So I have something like this with minus. So what this means is g of delta equal to that. So by doing that, so you can see that what I've done is I have written the bulk block and the boundary block as a sum over the blocks of double trace operators, blocks of the GFF operators on the boundary, plus double trace operators on the bulk. Sorry, these are the Witten diagrams. I use the Witten diagram equations to write G delta as a sum over the sum over boundary and bulk blocks of the GFF. Sure.
So the equation was that the W delta is equal to something.
Yeah.
Oh, but there were two things.
Yeah. So this is the basis. So what the point is that there exists a basis for expansion for any bulk and boundary blocks. The claim is there are functionals corresponding to these things. Functionals which are called dual to these guys. So these functionals are supposed to bring out these coefficients.
So is this some basis
Yeah.
or something? Is this a unique way of
Right. So yeah. So there is this issue of if this basis is complete.
complete or overcomplete?
Is it so? Yeah. The issue of yeah.
Not
Just
complete, but is it overcomplete?
yeah. Just give me a moment.
It is probably okay for this because the equation tells you that G delta has to be written one has to be able to write G delta like that.
Right. Yeah.
This comes from that.
Yeah.
Written
Right.
But is there a unique way of it?
Yeah, the question of uniqueness was addressed for. So okay, first let me mention that you can do a similar thing for for the usual CFTs Witten diagrams also. For the usual Witten diagrams, you have instead of G delta you have F delta, and instead of these guys you have F of double trace operators, and yeah, I know this answer, but I have to look at their paper once again, the Miguel and Dalimil, to answer this question. And so one important thing that they proved, so if I remember correctly, so they really said that the question of uniqueness is somewhat trivial. Right now I can't remember the argument, but the question of completeness had to be proved in the following way, is that if you have something like omega of delta times c, so if you have something like omega n delta and n, then only if it's complete, then so if this thing is complete, then you can exchange the two sums. Omega. And so this is something that they proved in their paper by looking at the tail of the OPE. But yeah, and so, but the question of uniqueness was something trivial, if I remember. So after the talk we can discuss this. Yeah. Okay. So let me write down the form of the functionals. What do the functionals look like? So the schematic form of the functions is as follows. We have omega equal to so now I pulled out of the hat this form of the functional. As you can see, it is. So if no one asks, I'm not going to motivate where it came from, unless someone asks. So are you asking? So okay, so in the paper by Dalimin Mazak, and also one of the first papers of analytic functions by Mazak and Paulus, they proved that a nice form of the functionals is as follows: is something like the discontinuity of fz with some kernel. It ran from 1 to infinity, I think. And so they proved that this form, this discontinuity is across the discontinuity across the branch cards of the conformal block. And they proved that this form is actually a very nice form that surpasses many kinds of functionals, and also it satisfies many the constraints of finiteness. And starting from this, by doing some contour rotation, so they arrived at this form, which is easier to work with. So this form actually comes from this structure, and this structure was proved to be, good for a very broad class of functions.
So what you write is W acting on F or H?
W acting on F.
And H
Actually,
has some labels.
I should really write G here, because I'm really working with G. So W of G is this.
And H is some labels, right?
That is right. That is right. H has some labels. And W's there are three kinds of functionals that I'm going to construct. So I'll call them alphas, I'll call them betas, and I'll call them thetas. And these three functionals will correspond to what extract the coefficients of these three blocks.
So this W is a linear function, right?
Yeah, it's a linear function.
So then this swapping thing is obvious, isn't it?
Now, since it's an infinite sum, you have to really look at the convergence. Yes.
These HIs, do they look like whose coefficients are to be obtained?
These HIs will look like,
HIs?
yeah.
For let's say the thing that gives you alpha.
Yes.
Is it related to G hat, delta phi plus 2n? Obtaining that, right?
Yeah, yeah. So,
Orthogonality type of thing.
I mean, H is going to.
Will you treat with the same block to obtain its coefficient or not?
I mean, the information for H comes from. So now I'm going to show how H is constructed, and it's going to be functions of the space-time dimension, and I think also delta phi. Yeah. So it has. Yeah, there are some inputs, but I'm not sure if I answered your question. But yeah, anyway, I think it will be clear. So the question is how to compute H Z. And this is the really last part of the talk. So yeah, oh shit, I erased it. So to compute Hz, remember that the properties of the functionals that I already wrote down, it has to satisfy finiteness plus swapping. By swapping, I mean omega on delta equal to delta of omega. So it has to satisfy the following properties. Also, I'm going to impose some orthogonality properties on the omegas, which amounts to the following. So just bear with me when I'm writing this whole thing. So I'm going to impose some orthogonality properties. And they are the following. By the way, here all these things I wrote down for the Neumann. For Dirichlet, these things will be replaced by +1s for all these things. So just sorry for not pointing this out earlier. Theta m claims. I will impose these constraints. And why I'm writing this? Because so that these things, when acting on the G delta, for example, if alpha is acting on G delta, alpha will give you an, just an.
So you're like, you're imposing this.
I'll impose this. The reason for imposing is so that they just pick out this alpha m is going to pick out the coefficient of G 2 delta phi plus 2 and G hat and so on.
This you write this as alpha prime.
Yeah.
Instead of G hat prime.
Yeah. So thanks for asking. So the functional corresponding to G primes is I'm calling them beta. I'll impose alpha prime to be 0.
No, but what is the prime of alpha mean?
The derivative with respect to delta.
So it's a partial integration?
Yeah, it's a partial integration. So alpha will depend on deltas, right?
No, I'm saying the thing, in order for this to do the job that you want them to do.
Right.
For example, in order for these B's to extract
Yes.
the coefficients that you want,
Mm-hmm.
you want B acting on the derivative of the block.
B acting on the
Beta acting on derivative of the block to be delta n.
Yeah, so but
now
it
you-
can be translated to derivatives also on. So yeah, that's a trick, because the derivative of the block is hard to compute. But when you really compute, but yeah, when you impose these constraints, you don't have to really compute the derivatives of the blocks. You can, when you impose that.
But beta prime is what you obtain by, so you assume that this has this form of convolution, and
Mhm.
then partially integrate the derivative on top of this.
Yes, that's right. And you can see that my equations in the end are going to be just beta is equal to 0, beta plus beta delta equal to 0, and then you can take their derivatives. They will give you some nice conditions on anomalous dimensions. Okay. Yeah. So the finiteness and swapping conditions, they amount to, so what they do is, so they constrain H's to be, so I'm just writing these things a bit schematically. So they will make H's as z goes to infinity behave like z to the power -1 minus eta, where eta is greater than 0. And then there are some other properties like when z goes to 1, they behave like 1 minus z to the power delta phi minus 1 minus eta or something like that. So there are some properties of H's that one can figure out from the finiteness of swapping conditions, looking at the convergence of the OPE. And so what you have to keep in mind is that the H's that I'm going to construct should have these properties, and also in the end, the whole functionals should also satisfy the orthogonality properties. And it's not, I admit that it's not easy to really come up with a nice H that satisfies all these things. There are also some other properties that I'm not really writing all the details here. And now how do you come up with an H that satisfies all these things? That's a bit of guesswork. And a nice H that satisfies this, so is some linear combination of a certain 2f1 function, which have the form something like and for integer k's and m's, you can really cook up nice ways so that all these things are really satisfied. These 2f1 functions, they actually satisfy all these nice properties. And yeah.
So at the very beginning you mentioned that you obtain this from like a particular solution.
Yeah.
Delta, and so where has that information gone in?
Sorry, so can you just repeat
So
this question?
initially, schematically doing
Mhm.
any extremal function.
Yeah.
You said that like if you knew one solution,
Mhm.
then you can construct and something. So where is that information?
That information is the following, that I constructed the basis from the solution I knew, which is the GFF. And corresponding to that basis, I have imposed the orthogonality conditions, and these decide what is the linear combination of 2f1s that I have to take.
So it didn't really come from the solution that you knew. It came from how a Witten diagram decomposes.
Yeah, but that is right. But the Witten diagrams were, so this GFF corresponds.
Everything was kinematical, right?
Sorry.
Everything was. I mean, you didn't quite. GFF didn't need to be a solution for this to work. If you had just Witten diagram decomposed in certain way, then you could always rearrange it so that you will get such.
Yeah, you can.
In other words,
That
if
is
you had
right.
another solution, let's say apart from GFF,
Yeah.
That can also be same.
but it will not be so straightforward, right?
Yeah.
Yeah, I mean, well, but
So supposedly A and B and TNs will be different, but it can always.
I think it means
I
that
don't know how
Yeah.
you would do this for other solutions.
Others- yeah.
This worked because of Witten diagram property.
the idea was that starting from GFF, I will. So why GFF? Because it's an analytic so it's something that you understand analytically. But if you really say that how to do this for another solution, I don't know how to do that. My goal is to explain the setup for just the GFF, which is
But the logic is the following, right? Let me just confirm that what I think.
sure.
So assuming your Polyakov bootstrap is correct,
Mm-hmm.
every correlator can be written as some more written diagrams
Yeah.
plus contact diagrams. Let's
Yes.
say exchange diagram, contact
Sure.
diagram. So let's assume that exchange diagram is a good basis for correlators.
Mm-hmm.
Now you have this written diagram, let's say in some mesh channel. You write it as a sum over blocks
Mm-hmm.
in the S channel as well as in T channel.
Yes.
Now that sum in the S channel should be equal to the sum in the T channel, which you can reorganize to say that an S channel block with any dimension
Mm-hmm.
should just be a sum of mean field theory blocks and their derivatives.
And S channel.
And that is what is giving you this extremal functional. This is giving you ability to decompose the solution in terms of mean field theory data, essentially.
That is
Essentially the coefficients of
yeah. That is the
block and
main
derivatives.
idea anyway. Yes, that is right. But yeah. But you asked me how to do this for any other solution.
Yeah, yeah.
That I don't know how to really do that. Yeah.
Sorry, I mean, where is this mean field theory thing assumption coming in?
So it just comes from, so you have a, let's say, written diagram. So you have a written diagram with an exchange of an operator of dimension delta, and you decompose that in terms of conformal blocks.
Okay.
And that decomposition gives you the conformal block of that dimension, as well as conform blocks of 2 delta phi plus 2n dimensions. It just, so there's
From
no
that-
mean field theory,
from
it's just
that,
kinematical package.
Yeah.
I see. That's what happens with one
Yes.
thing. That is always like 2 delta phi plus 2n.
Yeah, it's that block corresponding to this, whatever you are
And
exchanging.
that's what
Plus
says that is mean field.
Yeah.
Yeah, I mean, because the spectrum is that of the mean field theory.
I see.
And that fact is what allows, I think, this
Hmm.
technical construction. Because you write that equation in the S channel as well as in the T channel, then you forget about the written block. You just have the equation on the blocks now. So if you take
So
the
what do
written
you do
diagram,
if it is not on the main field thing, kind of, what happens to this argument about using written diagrams? If it is always like
yeah, any written diagram would decompose like this.
oh, so it just says that mean field theory provides a basis.
Yeah.
Yeah.
I see.
Yes.
And the property of mean field theory that is useful is I don't see that it is forming the solution, but rather that's what the written diagrams decompose into.
Yeah. So it's by
I see.
lucky that
Yeah,
it
so
really
you have
happens.
this S channel exchange written diagram. It decomposes into S channel mean field theory blocks
Right.
plus the S channel delta block, and in the T channel I think it just
Yeah.
decomposes into T
Yes.
channel mean field theory blocks plus their derivatives.
Yes.
So now when you take this and put it on that side, you just have now S channel delta block is equal to mean field theory blocks.
Yes.
Right?
Yes.
S in as well as in T channel.
Yeah. So in the usual case, we have something like sum over f 2 delta phi plus 2n. So you really have to consider not a single written diagram. You have to consider the exchange of ws plus wt plus wu, and then you have g delta from here, g of t delta from here, and the whole thing is f of z is equal to a sum over f2 delta phi plus 2n. So it's this kind of a decomposition that you get. Okay. So yeah, just to conclude, the concluding parts of this whole thing is that finally I will end up with the functional bootstrap equations, which are something like delta alpha acting on delta plus delta hat acting on delta hat equal to 0, and then two similar equations for betas and thetas. So these are the equations that I will get by acting on with this function on the bootstrap equations. And finally, let me mention that for Neumann, there is no beta 0 equation. Why is that? Because in order to, why is there no beta 0? Because you can never really find a linear combination of the two F1s that I just wrote here that also satisfies these nice properties, and you can never find them for the Neumann boundary conditions. And physically what this means is the following, is that there is always an ambiguity for the Neumann boundary condition, which amounts to the fact that whatever solution that you find for a Neumann boundary condition, you can always deform the solution by adding a solution from a contact diagram, because a single Witten contact diagram also is a fully crossing symmetric CFT solution, and you can always add that to any other solution for the Neumann boundary condition, and this is basically an ambiguity in the for any Neumann CFT Neumann CFT solution. Because the Neumann solution comes from adding a term like phi square to ADS, and this is 0 for, and it's the only thing that you can add. For Dirichlet you cannot write this because this is 0. Then it wouldn't be relevant deformation.
Relevant.
Yeah, that's what you need in order to deform it.
Why would it be? I mean, why does that matter? I mean, from the bulk point of view, you can just think in terms of effectivity, some effectivity, right? Which will give rise to deformation of the existing crossing symmetric solution.
Yeah.
Penadon's paper of 5 to the 4 classifies all the deformations up to any scale. You
Right.
don't need to concern. I mean, no matter whether it's relevant or irrelevant, all of them lead to some deformations of the CFT solution. So if you add some d phi term,
Yeah.
something like that.
Yeah. So yeah, I'm not really sure how to answer this, but yeah, maybe I'll think about this later and talk to you. But yeah. Yeah. So anyways, but in the end, the point is, I mean, you cannot really write a beta 0. One of the equations for the Neumann would be missing, and for the Polyakov bootstrap, we can you can add WC so that such that the equation the two systems of equations they match, so that the alpha of delta is basically the A of delta that was the coefficients of the Witten diagrams. So, and similar things for beta and B and theta and T. So this is, by taking care of that, we can add a Witten diagram, and for Neumann it's just a simple contact diagram that that is sufficient for this. And if you try to solve the Wilson-Fisher fixed point, this works. For epsilon square, there is no mismatch of solution.
Just a single contact.
Just a single contact diagram. Yeah, that's the end of it.
Any more questions?
So this fixes the ambiguity of the contact term?
This fixes the ambiguity of the contact term, yeah.
What is a good frame that people use for this problem? You know, in the usual case, you have
1D.
point at 0, 1, infinity, and then the z moves around, right?
Yeah.
So here you have a interface and boundary, and then you can fix this at 1 and let the other guy move.
Yeah.
What is the interpretation of that?
Okay. So interesting. Oh, so you can. So there is another crossing invariant that maybe is a bit useful to answer this is called a zeta, so xi, which is defined by 1 minus z by z, and okay, but I don't know if it will answer your question. So the xi goes to 0 limit corresponds to the boundary expansion, and xi goes to 1 is the goes to infinity is the bulk channel expansion. But yeah, I don't know. I have to think about this. How to interpret.
In 2D,
Yeah.
this cross ratio
Yeah.
is basically the cross ratio of the two object points and the two image points. So, so in the sense that it is like
Right, because it's reflected, it's always log to the one.
that's right. Yeah. But I don't know whether that works in arbitrary dimension. In 2D,
Mhm.
it is like that. I mean, it is the usual thing like Z1, 2, Z3, 4 divided by Z1, 3, whatever that thing is, in which now Z3 is to be interpreted as Z1 bar, and Z4 is to be interpreted as Z2 bar. And that's the cross ratio that
Okay.
appears in the formula like his.
Okay.
But his formula, of course, was very complicated.
Is there anything of defining some sort of a Ricci limit in which things should be well behaved, or rather, let's
Yeah.
say conversion formula?
Right. So Ricci limit is, I think, the limit of z goes to infinity. Sorry. So we said the question again. What was the question?
Yeah,
The Ricci limit is.
boundedness. What is the corner of the space in which the bounded limit should be found?
So at z goes to infinity is the Ricci limit, and I.
You don't have to do monotony, complex Z thing. Because in the usual case, you have to go like this and then go to Z equals 0. Because it's a Lorentzian problem, right?
Yeah, maybe I don't know. Here it's simple. I mean, here it's just that at the z goes to infinity limits, we know that the blocks behave in a certain way, and that fixes the h's.
I think it's different. Like
Yeah.
What they mean by Ricci boundedness is not the usual CFT Ricci thing. It's just some like a high Z going to infinity behavior kind of thing that we are looking at. That's it. Not our like monodromy and
I mean, the non-triviality of the edge boundedness is that is not that the blocks behave nicely. The blocks could behave badly, but their correlator needs to behave better.
Yes. Yeah.
Which comes from, let's say, chaos bound and things
Right.
like that. And that's what imposes constraint on the kinds of blocks that could appear. That's what at the end fixes your
Okay. Yeah.
Pocket terms
Uh-huh.
to be not very high spin.
Right.
Because if it spin more than 2,
Mm-hmm.
then you would get
Okay.
that boundedness.
Okay.
That's what
I see.
Any more questions? If not, let's thank you.